So today's lesson is about relations and functions. So we are starting topic 3. We just finished topic 2 test, and even though I haven't graded or finished grading the paper test that you just took, I know that the Galileo test was a big improvement from like your topic 1 test. So I have high hopes for this one. The whole purpose of letting you guys retake the test like in class, because remember the Galileo is like your test, and the paper one is like your retake. The whole purpose of that is so that you guys don't necessarily have to come after school on your own time to retake it. Now, if you want to, by all means, I have tutoring every Thursday, including today. But like, I just hate seeing kids waste their opportunity. I don't know why, like this class, if it isn't so bad, but I just see it a lot. Like kids that just like sleep or like stare off into space during the test, and I don't know. I just kind of like save that as evidence so that if like your parents ever ask like, what's going on? Why is my kid doing so bad? I'm like, this is what they're turning in for a test, and all it has is their name on it. Completely clear. So, you know, I give you retakes in class. Please use the study tools that I provide. Use your topic 2 review. Use the orange paper that I said you can use on your retake. Even though the retake isn't open note, write whatever you need to write on that orange paper so that you can get a good grade on it. All right, so keep that mentality while we're starting topic 3. Also, if you want to come to tutoring today, maybe you've come before and you already know how it runs. Maybe you don't know how it runs, but there's usually like more than a few kids in here. So we usually go through it as a group. So that way, if some people have like the same question, it gets covered at the same time. Like I'm not individually helping you, I'm helping everyone all at the same time. So if you're wanting to come in for a retake, you need to tell me that like right when you come in so that we can get you started on it and so you have the full amount of time. Don't wait like till the end to tell me you want to take a retake because then like tutoring ends and then you have to wait till next week. And don't come in and say, I don't know, I'm just here because I need to get my grade up. Like, okay, look at Infinite Campus and tell me what you want to do. Do you want to retake a test? Do you want to turn in some homework? I can help you, but like, I'm not going to spend time looking through Infinite Campus for you when I have other students in here that want help. All right, so come prepared if you do plan to come. And bring a homework assignment. Pull up an old test. I don't care what it is. Just come prepared. Any questions about that? All right. So objectives and success criteria. So maybe you have heard of relations and functions, maybe not, but it'll make a ton more sense after the lesson. But this is how you're being graded. So like, can you tell me domain and range from like a table or coordinates or maps or graphs, right? We'll go over all that. Can you distinguish between discrete and continuous data? Can you classify relations as one-to-one or many-to-one? I'm recording right now. It'll be in here for you later, but I teach this lesson every year. So I have a ton of like helpful tools if you want to check them out. This is from last year when things were online. I always provided like extra videos. So if you want like specific help, they're like shorter, right? And it says vertical line test, how to determine if a relation is a function. And so it's all in there if you want. The practice, so here's me talking about the practice every day, so don't say I never talk about it. All right, is going to be uploaded to Schoology. You have a paper, it says practice on it. That's the one that's your homework, not the notes. All right, the notes aren't what I want you to upload. I want you to upload the one that says practice. The notes you keep for your binder check. All right, so far the next binder check is scheduled for October 11th. So just hang on to your stuff in your binder. That's why it has 3 holes in it. Don't lose it. And your practice is what you upload to Schoology. If you ever need an extra copy, feel free to ask, but it's also uploaded in the link too. So there you go. here's the schedule so far for topic 3 assessments. So we're gonna finish the 3-1 lesson today, because I know a ton of kids are not gonna be here tomorrow because they're in clubs or something. Perfectly fine. If you're not here tomorrow, all we are doing is our homework and the exit ticket. Now, I think the exit ticket is super easy, especially because you get to use notes on it. So I'm still gonna give it to you, because that should be like easy assessment points. But if you're not gonna be here, I just leave it blank for the exit ticket score, and then whatever you score on your topic test, I put it in there. If you haven't noticed that, that's what I've been doing. So, just study, prepare for your topic 3 test. If you're not gonna be here, make sure you do your homework if you're not going to be here. Any questions? All right, that's all we're doing is working on our homework and our exit ticket. So now let's do our notes. So have this paper in front of you, not the one that says practice. It says 3-1 relations and functions. All right, so relations. Let's fill in the blanks here. We have a relation is a set of ordered pairs. It may or may not be a function. And it can be shown in a ton of different ways, but it's basically a set of ordered pairs. So it could be like the first example, it could just be a set of ordered pairs, like a list. You should know that ordered pairs go in the order of X, Y. You should know that from your last test. So that's what a set looks like. Here's what a map looks like. All right, so in the maps, they don't repeat the numbers, like they don't write repeating numbers, even if they're there. They just put arrows, and if it's like the coordinate is 0, 1, and 0, 2, then they'll just draw another arrow to point to the 2, if that's the case. Or if it's like the other way around, like maybe 2 numbers point to the same number, then they'll draw an arrow showing that. I haven't seen that you guys have to make a map, but I know that was a question like on previous tests like last year. So just FYI, don't write the repeating numbers in your map, just draw a second arrow. And then we have a table. And then we also could have a graph. So I'm going to have you fill this in. We could also represent it as a graph. And those graphs could either be continuous. So I'm just drawing a random example. There's a ton of ways I could draw a continuous graph. But like a continuous graph doesn't have like any breaks in it, if that makes sense. Like it continues. That's like filling up a swimming pool, right? I could measure it at any point. I can have like fractions of numbers, and that's totally fine. But then we also have discrete graphs, which would look basically like dots. Like separate data points would be a discrete graph. And that type of data would be, say, like shoe size, right? Like it's either 8.5 for your size or 9. It's not 8.75. Not 8.99. It's like this or that. That's like the difference between the types of data. But we'll talk more about that later. Questions so far, just on like the different forms? All right. So scrolling down then. We have domain and range. Really important, you know the difference. So domain, I know it's scrolled back up, I need to scroll back down. Domain is a set of all X values in a relation. And the range would be all of your Y values. So an easy way to remember that is what I've used in the past, which is Dr. XY. All right, that'll help you remember that your domain is always your X's and that your range is always your Y's. So if I'm looking back at the examples up top, what would be my domain of the set? Just read them out. Good, 1, 3, and 0. What would be the range of the set? Good, that's all we're asking of you. What would be the domain of the map? And the range? Good, so you know the difference between input and output then, without me even having to tell you. All right, you know that X's are your inputs and Y's are your outputs. Same with table. Now for graphs, the domain is a little bit different. So if I'm writing the domain of these ones, I can just make a list, right? It's either this number, that number, or this number. But for a continuous graph, it just depends on how the graph looks. So let's say it goes on infinitely in both directions. In that case, I would say that my domain is all real numbers, right? Because when I look from my X's, like this way and that way, it goes on infinitely, right? So it's all real numbers. For my Y's, for my range, that's the up and down axis, right? The Y to the sky. Well, it looks like my highest point is here, and my lowest point is like here. So if this Y value is 6, for example, and this one is 3, then my range is all numbers from 3 to 6. So there's like a constraint on there. And we'll do more examples with that like later this unit, but I'm just making you aware. Sometimes it's a list. Sometimes it's an inequality, like if it's for a continuous graph. Discrete graphs, you kind of treat them like a set. Like, right, these all have very specific coordinates. X's and Y's, domain and range. Questions so far? All right, so then let's do some of these examples. What is the domain of this function? 1, 2, 3, 4, and 5. Good. Here's how you write it. There's like a fancy bracket that I think is on your Chromebook, but it looks like this. That's what goes like on the outside of your list. And then inside, you're just making a list. When it's discrete data, when it's not like continuous data. So it's 1, 2, 3, 4, and 5. And then close it with another little fancy bracket. The numbers don't necessarily have to be in order. Some math teachers will say that it has to be. Honestly, it's just a list. You're just saying the domain is either this number, or this number. Sometimes on a test, though, you have to read the instructions carefully. If it wants them in order, then put them in order. What would be the range of this function? 11, 12, and 13. Do I write 13 3 times, even though it appears 3 times? No. So if you did, just erase it. Only write it once for each time it appears. I'm sorry, I have problems trying this stuff. All right, so do not write repeating numbers twice or something like that. Do not write repeating numbers more than once. That sounds better. All right, do not write repeating numbers more than once. Questions? All right, so then scrolling down. What would be the domain of this function? 2, 3, 4, 5, 6. Good. So again, write your little list with your fancy brackets. And then the range would be 0, 1, 2, 3, and 4. All right, for the student example, we have to fill in some blanks. So I'm going to put what the student example looks like. So not this one. This one. All right, so fill in the blanks for your student example. And then identify the domain and range. All right, so what is the domain of this function? Good. Now, are -3 and 3 the same number? So yes, you do have to write them both. I did have that question earlier. Just think about it as like a balance in your bank account. There's a big difference between having $3 and -3. So yes, just list them out. Don't write any repeating numbers. For your range, it'll be 1, 3, -2, 2, and what was that number that was in here? 6. All right. Any questions? Make sense? Yes. You can put the numbers in order from least to greatest if you wanted to. I've never seen that it's like a rule that you have to. And I've talked to other math teachers and some say it is, some say it's not. It's just a list. I just write it how I see it. Questions though? All right, so then now those are relations. Let's talk, that's domain and range. Now let's talk about functions. So a relation is a function and each x value has only one y value. Read that very carefully. It's not saying that if each y value has only one x value. So I can have y values that repeat. But I cannot have an x value that points to different y values. So if you look at your set of data and you see that there are no repeating x's, so no repeating x's, then you know that it is automatically a function. You don't even have to look at the y's in my case. So no repeating x's. It is automatically a function. If there are repeating x's, then you have to look at the y's. If the y's are different, then it's not a function. If the y's are the same, so let's say in my set of data, I had 10, 15, and 10, 15, right? It's the same y value. So it's still technically a function. Does that make sense? But if I change that y value even a little bit, even if it's like 15 and a half, then now it's not a function. And the way that I think about it, it's like when you did your input-output tables in like elementary school, there's a rule that went with that table, right? You were either like adding 5 or multiplying by 2, or maybe doing a bunch of other things. I just think of it that way. There's no way I can like multiply by 2 and get 2 different answers. Make sense? All right, but now let's look at these examples and figure out if their functions are wrong. So the maps for this first one, are there any repeating x's? So is it a function? function. And again, the maps don't write like when it repeats, it just draws an arrow. But all the x's have only one arrow coming out from it. This idea. Okay. Bye. All right. Now look at the second example. Do I have any repeating x's? Let's see again. Remember, the maps don't write down the repeating numbers, it just draws arrows. So which number repeats in that one? 2. In that case, then you look at those y values. Are those y values different from each other? So is this one a function? Good. So not a function. Questions? All right, so that's how you can tell from a map, but still each x value should have one y value. So if every x value in a function gives a different y value, is it a function? No. Think about it. Yeah, if each x value in a function, that's kind of, they probably should have eliminated that. But if each x value gives a different y value, it is a function. It'll be fine. It's not very All right. If 2 or more x values in a function give the same y value, so we have 2 or more x values in a function that have the same y value. Is it a function? No. Okay, so it is not a function. Wait, I think I messed up. Let me backtrack. I read that as carefully as I needed to. All it's saying is that 2 or more x values give the same y value. Is that allowed? Can I have, as long as the x values point to different numbers, that's fine, right?
Yeah.
If they point to, if like all of these numbers pointed to 15, is that allowed?
Yeah.
So it actually is a function. Sorry, I was not reading that the way it is written. So erase that. It is a function. Because think about it. What if the rule for the table is that you're multiplying by 0? Aren't the outputs all going to be 0? No matter what the input is? So like, that's how I think of it. Questions? All right, so then let's look at these examples. This first one looks really familiar. I'm not sure if it's like different at all, but is that what a function? Yes. I probably should have changed. What about the one right next to it? Is that what a function?
Yeah.
So it has to be, look at your x's, don't even look at your y's until you're done looking at your x's. Are there any x's that repeat? X's are inputs. No, each x points to like one single number, right? Not like different numbers. So this one is a function. All right. If you look at your x's and none of them repeat, then you know it's a function. If you're looking at your y's and you probably looked at this and this is what confused you, you don't even need to have gone that far because you saw that all your x's point to different numbers. Point to one number. All right, they are allowed to have the same y value, but can't have x's that point to two different numbers. All right, questions? Does that make sense? All right, so yes, both functions. Is there something else on that page? Okay. So this page now. Is each relation a function? If so, state whether it is one-to-one or many-to-one. So first, look at your x values. That's always the first step. If you're figuring out this function. Here are all of my x values. Are there any repeating x values?
No.
So what does that mean?
A function.
It's automatically a function. I don't even need to look at the y's. So yes, it's a function. Now to figure out if it's one-to-one or many-to-one, then yeah, you do need to look at the y's now. Are there any y's that repeat? No. And I'll just kind of highlight it in a different color for you. Nope, there's none that repeat. So is it one-to-one or many-to-one? One-to-one. Right, many-to-one would be like if there's different x's pointing to the same y. And you will be asked something like that on the test, just FYI. Like your exit ticket. It'll say, is this relation one-to-one, many-to-one, one-to-many? Just think about it. All right, class example. Is this one a function? More than one person?
No.
And what tells you that it's not a function? Good. The fact that this points to two different numbers is why it's not a function. And then how would you classify this one? As one-to-one or many-to-one? Good, because we have one x going to, so one x going to the same number. That makes sense. So actually what tells you that it's many-to-one is that there's multiple numbers pointing to the same number. Does that make sense? So there's multiple numbers pointing to the one. So that's why it is many-to-one. All right, keep scrolling. Now the student example, I'll have to give you the info so that you can solve it. Hang on. All right, this one. So fill in the blanks and then answer the question. Questions? Here's the solution. Now next page, the one or next other side of that page. About the vertical line test. So the vertical line test states that if you can draw a vertical line through any place on a graph without touching more than one point, the graph is a function. So that's basically a way to say each x has one y. If I draw a vertical line, each x should only have one y. There's a y. All right, now the only problem with this one that I see students make is they just can't remember if it's a vertical or a horizontal line test. All right, it's a vertical line test. So just, I don't know, put it in your brain. When we were doing stuff on the last test, vertical lines always had the formula x equals, right? So each x should only have one y. So here's how you do that. You're just going to like take your pencil, or like if you can envision it on your test, like if it was on a screen, like you drawing vertical lines, and sorry, it's hard to draw vertical lines here, but draw vertical lines through your graph. Right, just draw them through your graph and make sure that the graph touches at one point on each vertical line. So like it touches this vertical line here, touches this vertical line here. Is there anywhere that I could draw a vertical line on this graph where it touches 2 points on the same line? So then is this a function? Yes, it passes the vertical line test. Will this one pass the vertical line test? No, but you could try drawing your vertical lines again. Not very good with vertical lines. All right, but you can already see, like even if I have a vertical line here that it passes on, it just needs to fail one of these. All right, so it fails on the second vertical line, so that makes it not a function. Try both the student examples. Figure out if it passes your vertical line test. All right, so on a side note, thinking back to what we talked about right at the beginning, for this first student example, what type of graph is it? Discrete or continuous? Good. All right, so I'm just gonna kind of write that in here so you guys can get more used to classifying them. But this is an example of a continuous graph, because it's a line versus like a dot. And did this one pass your vertical line test?
Yes.
No. So just look at it carefully. I kind of thought that it might fail. But like you see how as it goes up or as it goes down, like it gets a little bit wider. Yeah. See that? So it technically does pass. All right, if it was going like straight, you know, up and down, or like if it was like flipped to the side, then it wouldn't pass. But it actually did pass. And I was like skeptical, but I looked at it more closely, and it is a function. But do you get like the general point of it?
Yeah.
All right, it should only touch one time on each vertical line that you draw. Is this second one a function?
No.
Where does it like not pass? Good, so it's saying that this 4, and I'm horrible at drawing lines, but this 4 has more than one y value, so it does not pass. It fails the vertical line test. What type of graph is this one? Discrete. All right. So it fails here when I drew my vertical line. Questions? All right, so then scrolling down. So we're going to kind of switch to like a different topic. Now we're going to talk about reasonable domain and range. All right. We kind of touched on like these types of concepts on the last test, right? When on the last test, when we were talking about buying like 8 packs of juice or something like that, was it possible to buy 7.5 8-packs? No. So even though like that answer worked when you plugged it in, it wasn't correct because it's just not logical. So it's the same concept with like reasonable domain and range.
It wouldn't make sense anyways. What are you gonna have them like if you buy 1.5 milks? What are you gonna have them cut the other half of the milk?
Exactly. So like you can't buy fractions of stuff. Like I can't buy half an apple, right? So this is the same concept with that. Same with like, can I buy negative of something? No. So same thing like that. So reasonable domain and range requires us to think about what makes sense in the context of a word problem. So like, imagine you buy a movie ticket and they each cost $5. Can I buy 2.5 movie tickets?
No.
No. Can I buy -6 tickets?
No.
Can I buy somehow without tax, like $18 worth of tickets? No. Because in this example, they all cost $5. All right, if you think about tax, yeah, probably, but like in this context, no. So for this specific example, my domain would be like the number of movie tickets I buy. So like it would be positive integers, like I can't do negative tickets and things like that. If I was talking about the cost, like that would be my range. It would be in increments of 5. So like 0, 5, 10, 50, 20, and so on. So we're on the last page now. We need to find or write down a reasonable domain and range for each function. So we have a hose fills a 10,000-gallon swimming pool at a rate of 10 gallons per minute. So to help you figure this out, think about what your graph would look like first. Like with the labels and everything. We're filling up a 10,000-gallon swimming pool at a rate of 10 gallons per minute. Would the graph be continuous or discrete? It would be continuous, right? Because you are like consistently filling it up. Like it's not like you're filling it up. I don't even know how to describe it. Like, yeah, like it's just, you can measure it at any point, how much water is in there, or like how many seconds. Like it just continues. Versus like shoe size or something like that. So it would look something like this. And your x-axis is usually your independent variable. Maybe you know what that means, maybe not. But like, it's usually like a time. So like this time it would be minutes. Because the minutes aren't affected by how much water you put in there, right? It's the independent variable that goes on your x-axis. Your y-axis depends on your x-axis. So like how much water is filled in depends on how much minutes have passed. Does that make sense? Okay. Gallons of water is my y-axis, minutes is my x-axis. And then remember, domain and range, Dr. XY. So my domain is my x's or my minutes. So would it be reasonable to start my domain at like a negative amount? No, it wouldn't be reasonable. What would be a reasonable number to start at? I think there was a line. Sophia went and then you'll be after her. So it'd be reasonable to start at 0. And I'm just going to kind of write it and then explain. All right. For continuous graphs, it's an inequality versus like a list. Because, you know, it continues, right? So for continuous graphs, we do inequalities for the domain range. But it's basically this type of setup. So it starts at 0. And where would be like a reasonable endpoint? So this is for the minutes, right? Does it take 10,000 minutes? It doesn't take 10 minutes. So you have to do like a little bit of math. 1,000, right? Because it's 10,000 gallons total, and it's going at a rate of 10 gallons per minute. 10,000 divided by 10 is 1,000. And you will have to do that on your topic test, just FYI. Like a little bit of math, not anything too crazy. All right, but would it have been reasonable to end at like 1 million for the domain? No, that would be way too much. Now the endpoint we figured out by like calculating it, but would it be like reasonable to do way less than that, like 500? Right, that wouldn't be reasonable either. So this is a reasonable domain. It'll take about 1,000 minutes to fill it up. Now for your range, it's going to be a similar setup, but now we're talking about gallons of water. So where's a good like starting point? Would it be a negative number?
No.
Can it be 0? Yeah, we can start at 0. And then instead of writing X, what am I going to write? Y, because it's our range. And then what's a reasonable number to end on? 10,000, right? Because we don't want to overfill the pool. That's the maximum amount it can have in there. So that's a reasonable place to end. Does that make sense? All right. So then that's for continuous graphs. So I would just write this little note that continuous graphs or continuous data, so graphs/data, use inequalities. All right, continuous graphs/data use inequalities for the domain of range. All right, next example. We have a restaurant needs to order chairs for its tables. One table can accommodate 4 chairs. So think about how this data will look. Will it be more continuous or discrete? Discrete, because can I buy like a fraction of a chair?
No.
No, so that's why it's gonna look more like dots. And probably something like this. What is my x-axis gonna be labeled as, you think? Will it be chairs or tables? Chairs. So it's whatever is independent of the 2 variables. So it's going to be number of tables. Because the chairs that you buy depends on the number of tables, right? So that's why the chairs goes on the y-axis. Aiden, you only have 10 minutes left. All right, so then for our domain, since it's discrete data, it's more like a list, or it can be like a description. So discrete data, I'm just going to say, does not use inequalities. All right, usually it'll say like all positive integers, or what else? All real numbers, or increments of 4, something like that. Or they might have a list. So we'll do a list. So for the domain, that's X's or Y's? X's, and we said that the X represents tables. So what's like the minimum tables you can have?
1.
1, or you can even start at 0, but we could start at 1. Less than or equal to X, less than or equal to, what's going to be like a good endpoint? Would it be reasonable to have like 1,000 tables? No. So 10, 20, it kind of just depends on the size of the restaurant. So it doesn't say, I would think that 10 might be too small. Maybe 20, maybe 30, just to be like safe.
Maybe 1,000.
25, I think 30 might be reasonable. We don't know how big this restaurant is. They should have told us. So let's just pretend about 30 tables should be more than enough. It's not unreasonable. All right. The range, oh, I keep writing it as an inequality, but it's not, sorry. Sorry. I'm just like used to it. So, sorry, we're gonna make this a list instead. So we start at like 1, and then 2, and then 3, 4, and then we could put like some dots that it just continues in that direction. Does that make sense? Sorry, I made a mistake. We don't use inequalities for discrete data. For domain, it might also say all positive integers. So you can just write that in there too, in case that pops up on the test. Now for the range, what's like the minimum numbers of chairs that I'm buying?
4 chairs.
4, because if I buy 1 table, it's 4 chairs. Is it gonna go like 4, 5, 6, 7? That wouldn't really be reasonable, right? It'd be 4, 8, 16, and then it can keep going, right? Until it's like no longer reasonable, right? All right. All right, and it might also be like ranges, increments of 4. Okay, or like positive increments of 4. Try the student example. Try making a domain and range for your student example. How this graph would be labeled. So Bowler pays $2.75 per game. So what would be labeled for my x-axis? So my x-axis is normally the independent variable. So it's actually going to be number of games on your x-axis, right? Because the cost would depend on the number of games, right? So the dependent goes on your y-axis. Here's how I usually remember it. You can make a D with the y-axis. And the independent normally goes on your x-axis. So dependent, so you're not confusing domain, and independent, and I'll just abbreviate it. All right, so that's basically how your graph looks. Now, is it continuous or discrete? It is discrete because can you buy like half a game? No. All right, now the domain, and I don't think it's a rule that like discrete data doesn't use inequalities, because I'm looking at your text and it's discrete data, but it's in an inequality. So I don't think it's a rule, I guess, because they don't usually write it like that. All right, but the domain for number of games, like what's a reasonable domain? 1. So starting at 1 and ending at maybe like 10 at most. All right, good. But it's basically whole numbers, right? Like 1, 2, 3, no fractions. So all positive integers. Now for the range, I would say all positive integers up to like 10. For the range, what would it start at? And then continue going up by, you guys know like the next one, I think it's 550. And then the next one is like
25.
good, and then it just keeps going up. Right, but increments 275. Questions? All right, so we finished the notes today. We finished the notes today. Tomorrow, we are just working on the assignment and the exit ticket. So if you're not gonna be here, then you need to get it done